Hello, everyone. Welcome to this presentation, and thanks a lot for joining in. And what we're going to do today is I want to introduce to the community a new set of forecasting tools that we have developed at the Weather Prediction Center International Desks. Actually, we have developed these tools in the last, I would say, 2 to 3 years, but we have put a lot of work on these in the last year or so. So to start the presentation, I want to point out to the mission of the international desks. And the main mission is to enhance the weather analysis and forecasting practices in the region, mostly through training. But aside from the training, we also do other stuff like developing different tools that enhance the weather forecasting. These tools are specifically tailored for regional needs. So the way we develop the tools is we coordinate with the different weather services, see what are their needs, what type of weather phenomena they're interested in trying to resolve better, and we put emphasis on developing those tools in coordination with them. And and these needs are mostly for weather services in the Americas, which are the WMO regional associations 3 and 4. So we work not only with the US, we also coordinate with people in the US, but mostly with everyone that is south of the US. So Mexico, Bahamas, Cuba, all the Caribbean, Central America, and South America. This is just an example on the right. You can see a figure showing the Galvez-Davison index. For those of you who don't know this, Mike Davison and I developed this between 2012 and 2014, and we developed the official manuscript in 2016. So people have been using this index all over the world actually right now. We're pretty happy with that, and the results are pretty positive. So before I move into the tools, since we're speaking about the GDI, I just want to remind you about it because one of the tools uses the GDI. And in a nutshell, the GDI diagnoses the environments favorable for different types of tropical moist convection in the tropics and subtropics. So it was designed most for the Caribbean, but it is applicable in most of the tropics. So the GDI is a sum of 3 different indices. First, we have the column buoyancy index. The column buoyancy index describes the amount of heat and moisture in the column. Then we have the inversion index, and the inversion index describes the effects of the trade wind temperature inversion on drying and stabilizing convection. And finally, we have the mid-level warming index, which describes the effects of the thermal aspects of the mid-troposphere on stabilizing or destabilizing convection. So what we can see on the right, this is just a schematic figure of what the GDI looks into. And the green would be the column buoyancy index value. So whenever we have these very warm and deep moist columns, then this value becomes high and the GDI becomes high, which suggests that we have the potential for more convection, right? For deep convection and higher rainfall amounts. Then if you look at the inversion index, this is an example of a strong trade wind inversion. And when you have a lot of warm and dry air overlying moist air, and we have a sharp gradient, right? This shows up in theta E, and the GDI gets it. So whenever you see these very dry air masses and very stable inversions, the GDI will be very low. And this corresponds to these shallow cumulative regimes. And then you have finally the mid-level warming index. And this is just based on the temperature of the mid-troposphere. So whenever the temperature is warmer than -8, this index becomes more negative, meaning that the potential for precipitation starts decreasing, right? Okay. This is in a nutshell what the GDI is. Before I continue, I want to remind everyone that we have 5 different tools and we only have 1 hour. So I will only be able to show the generals on the different tools and will not be able to go into details, but we can do that later on as the year goes through. We can maybe arrange some other session for a more detailed analysis. Okay, so GDI resources. The GDI website is this one. And this presentation is going to be made available, so you don't need to write everything down. And In the website, you can find the manuscript. You can find experimental forecasts. If you see, you can see that there are forecasts for 0, 0, 0, 6, 12, and 18C, so all the cycles of the GFS model, and for different parts of the world. So we have North America, South America, even Africa, Asia, and maritime continent, and the Pacific Basin. Then this website also contains the code for wind grids. So if you're using the software wind grids, you can grab the code and code the GDI. And also we have coded the GDI thanks to Mark Klein. We have coded the GDI in using European model data, and this has been working great for us. It's been working particularly good in the Americas. However, since this is in internal use, because as you know, this is now the European model data is now a NOAA product, so we cannot really share it with everyone. Okay, so this was an introduction showing what we did with the GDI, but we have developed a new set of forecast tools. And this set of forecast tools is the following. If you see here on the left, we have the enhanced GDI, which is a very similar version to the GDI with some minor enhancements. But the algorithm also contains additional information. It contains, for example, you can see the winds plotted at key levels. You have moisture convergence, upper divergence, and so on. Then we have the trade wind inversion diagnosis algorithm. We're also going to show that. We have a severe weather potential algorithm, which is being very successful, especially in South America. And then we have a surface front identification algorithm. I know a lot of people are using it right now. Even TAFB in the National Hurricane Center are using this to help them identify surface boundaries in the Caribbean Basin. And then we have the Central Andes precipitation algorithm. So I wanted to point out that these algorithms have been programmed using the WindGrid software. Mike Davison and I know that many people are fans of this software. WindGrid is freeware. It's open source, and it's developed by Jeff Kropp. He works at NOAA, but he does this in his free time. So we want to acknowledge Jeff for all the work developing WindGrids, because this has made this possible. We rely a lot on WindGrids because it's very versatile for analyzing gridded output, and it's designed for Windows. And as you know, a lot of people have a Windows laptop, so it's very easy to install and to run on Windows, and you can do a lot with it. All right, so how to access these new diagnostic tools? These are online, so you can see the link here, and this is how the website looks. And we're going to go a little bit into the website as we go through the presentation to see examples of the algorithms compared to real life situations. So you can access this website, and the output, we are using GFS output of 00 and 12 UTC. So it's continuously updating with the cycles of 00 and 12 UTC. And if you can see the websites, we have 12 domains that we have made available for the Americas. However, not all tools are coded for all of the domains, and implementation decision is upon tool skill. So for example, the GDI doesn't work really well in southern Chile, right? So we haven't put a lot of emphasis on that. And for example, the hail and severe weather algorithm doesn't work perfectly in the equator. It's not designed for those regions, or some of the equatorial domains don't have that implemented. Then another thing that I wanted to point out is that the tools are still being validated. So there is always a room for improvement. So we welcome user feedback. And it's thanks to you, to the users, that we can make this better. So at this moment, we have reached a level that we're very comfortable with the tools that we have. But we're still open to feedback to improve them in the coming months. Then as the weather changes constantly and we run, you never get bored, right? And we're continuously running into different weather situations. We're still learning the best ways to apply the tools into weather forecasting practices due to these changing weather scenarios. And since this is a work in progress, this is just an introductory presentation to expose you guys to what we have done. We're still working on building thorough documentation. So we don't have like a published journal article on each tool yet. We're still way behind that. All right, so this is an example of the Caribbean domain tools. So for the Caribbean domain, where we have our work has a lot of impact, we have 4 tools available. We have the enhanced EGDI, we have the trade wind inversion macro, we have the severe weather algorithm, and then we have the front, right? And as you can see, for example, we don't have the copy here. The copy is the central precipitation index because it's not relevant, right? So the amount of tools, the tools that are set for each domain will vary depending on applicability. All right, so these are the tools that are going to be introduced today. We only have 45 minutes at this point, but thus the emphasis is going to be placed on these 3, on the 3 in the middle. So I'm going to briefly introduce the enhanced GDI. Then I'm going to talk a little bit more about the trade wind inversion diagnosis twin. Then I'm going to move into the severe weather potential, and specifically hail, which is called GR02. Then I'm going to move into the surface front identification. And finally, I'm just going to touch very briefly the copy, the central Andes precipitation accumulation index. So key points to consider when using the tools. This is very important. So the first point is that these are diagnostic algorithms, right? So they depend on the quality of the graded data set. So if the model, for example, at this point we have them coded in the GFS, right? So if the GFS fails resolving an atmospheric structure, then the tools will fail as well. So they're depending on the source of the data, right? Then something else that is important is that they are designed to point the forecaster into potentially hazardous weather, not to tell a detailed story of the factors producing the event. So the idea of these tools is that when you come in the morning, if you're a forecaster and you don't have continuity and you need to try to realize what's going on with the atmosphere because you just came from a break and you don't know. The idea of these tools is that just by looking at them, you have a quick, good idea of which regions you need to pay attention to. They will not tell you exactly what are the effects of the shear or the effects of the buoyancy or the amount of precipitable water available, but they will just tell you, give you a general idea of which areas you need to look at and during which time frames. So how to gain confidence on the tools? A way to gain confidence is by cycle to cycle consistency. If you see that an algorithm is producing an output very consistently in continuous updates of the model runs, that will give you more confidence that might materialize and you need to look into that. Then something else is that intercomparison with other models is also very important. So this is, at this point, we only have this coded in the GFS, but it's good to look into other models because as good as a model can be, the model can be really wrong. Other things that are very important, and this puts a lot of emphasis on the work that Mike and I do in the international desks, is both knowing the climatology of the region and the relationship of the phenomena with the weather pattern. So if we're looking into a severe weather event, and we are in the middle, say in the middle of January in the central US, then you need to be a little bit wary because for the most part, severe weather events don't happen in the peak of winter, with exceptions. So that gives you an idea whether or not believe a tool. And then also relationship with the weather pattern. So you're going to see that in some of these tools, we have some layers of flow that we consider that are key for a weather event. So for example, in the severe weather macro, we have the upper level flow to have an idea of the role of the upper jets. And we also have the 850, 925 flow to have an idea of the role of the low level jets, which are very important for severe weather. All right. As I mentioned, they're currently coded using the GFS model data only. So GFS is a Nuevo product and is very easily available to us and fully available as well. They're not coded in other models yet. And they're currently programmed using only and available online. So they're not available in an AWIS at this time. I know there's interest in developing some of these tools in AWIS and AWIS, but we haven't been able to get there yet. We started with wind grids because our target audience are Latin American weather services, and most of them don't have an AWIPS and AWIPS. And wind grids, a lot of people are very comfortable with wind grids. Okay, so this is a graphical view of the 5 tools we're gonna speak about, and as I mentioned, the emphasis is gonna be in the twin, on the severe weather algorithm, and in the front identification algorithm. All right. Before I move into the tools, I want to acknowledge some people who have been key for the developing of these tools. One of them is Nestor Santayana. He's a forecasting chief at the Uruguay Weather Service. And Nestor has been a key developer for the severe weather algorithm. I remember that Nestor trained with us at the international desk in 2012, and he had already brought in ideas for hail forecasting in South America based on observations and analysis of model analysis during those events. So he already had some ideas and some parameters he looked into, and then we combined the efforts of Nestor with Mike Davison's and I and our efforts, and this resulted in a little bit of the first hail algorithm. It was called GR01, and the name is weird, but GR stands for granizo, which is hail in Spanish. So granizo version 1. And this was very successful since 2015. This evolved into GR2 in 2019 since there were some changes in the GFS model. So we revisited the algorithm. And then eventually we worked around the end of 2019 into early 2020, trying to make this a little bit more, I would say, general for depicting different types of severe weather, not just hail. So I'm going to speak about this one, GR02, which is a more complex version of GR02T, which is a much more complex version of GR02. So thanks to Nestor, he's always helping us to improve and validate the algorithm. I know he's present on this presentation. Someone else I wanted to acknowledge is Jeff Krupp again, but Jeff Krupp is instrumental for this because he's a wind grids developer, and Jeff coordinates directly with us and even comes to know us sometimes to the international desks to sit with us and ask us what would we want for him to develop in wind grids. So how can he make wind grids better based on on our needs and on the needs of the community. So yeah, I wanna acknowledge Jeff because he was able to develop wind grids to a level that we can now we can run it automatically and have these scripts produce the results automatically on a daily basis. And then finally, I want to acknowledge all users because thanks to their feedback is that we can improve our algorithms. If we don't know if they're working for you guys, then we cannot really do much. But your verification and your feedback really helps us to make this work better. Within the users, special thanks to Manuela Sanchez from the Argentina Weather Service. She's been also instrumental for the validation of the hail algorithms in Argentina, and also implementing this in routine forecasting practices as in the Argentina Weather Service. All right, so we have 5 tools to talk about, and we have 40 minutes. So we'll see if we can do this successfully. So the first one is the enhanced GDI. This is enhanced. GDI is the Galvez-Davison index, and E is for enhanced. And we have developed this about a little bit over a year ago. So the EGDI, the index itself, is very similar to the GDI, but it has an additional set of quantities that we realize that are important for tropical convection. So the GDI itself is a purely thermodynamic index because it doesn't have any wind information at all. However, the EGDI has variables that contain wind information. So we have moisture convergence, and for this you need to consider the winds. Of course, upper divergence and upper convergence as well. Right, so this is not a purely thermodynamic index anymore, and it's a hybrid between a thermodynamic and a dynamic index. Right, the way we developed this so far has been empirically. We've been looking at the evolution of convection over many days during rainy season in South America. playing with different values until we came to we came into a set of values that work really well for us. So these additions to the GDI are the following. So we have the moisture convergence in this particular layer, 950 to 700, and this is very important because this speaks of the triggering of convection. The GDI itself, which are the black dots, only talk about the environment. But these, mixing ratio flux convergence will speak about what if the low level flow is pushing moisture together and helping to trigger convection. And this is very important in the tropics. I was actually in Barbados. I know Steve Goodman is also in this presentation. And we were in Barbados a year ago during a workshop in July. And it was my first time in the Caribbean, which is ironic. But I was there and I was looking at the different algorithms and the output and what matter and what not. And I realized that low-level moisture convergence is very important in Caribbean convection, and sometimes we would even overwhelm the GDI. So we decided to look into implementing this into an algorithm, and the EGDI has that. Something else that we implemented are upper convergence. Upper convergence is the orange, right? And this layer worked out really well for us. And sometimes what happens with tropical convection is you will get this dynamically induced upper convergence, and that will generate an elevated inversion and limit the vertical development. And that has an impact in rainfall amounts. So that is very important, especially in tropical continental South America. So we realized that adding this improved the forecast of the GDI. And then finally, we also added relative humidity in this layer. This is not 700, this is 400 to 300. And that also helps us visualize whenever you have an elevated inversion. And those elevated inversions can have an impact in convection. And that is very common in Western South America, Western tropical South America, especially when you have westerly flow, when you have a subequatorial upper jet that enters the continent, that will tend to induce these elevated inversions and limit convection, among other things. And then finally, we have a precipitable water enhancement. And the precipitable water enhancement was mostly because we realized that some regions are very sensitive to the amount of precipitable water itself, which makes a lot of sense. One of them is the Caribbean. And whenever we get P1 values over 30 millimeters and more, usually that correlates with enhanced rainfall. So just by considering these additional four factors, we came out with a new quantity that has been working well for us. Okay, so this is a plot of the enhanced GDI, and you can see we have a legend under each of the plots in the website. The enhanced GDI itself, the EGDI, the values are kind of similar to the GDI. It's a dimensionless index, and you can see on the scale whenever you start seeing light blues, it means that the environment is favorable for maybe one or two very isolated thunderstorms. And then once you start getting into the greens and especially yellows, then your potential for thunderstorms is higher, right? And once you get into the oranges and reds, you start running into a potential for locally heavy rainfall. So this is just the shaded colors, but the algorithms, thanks to the work of Jeff Kropp, have other stuff in them that will help us to make a decision when we do weather forecasting. So for example, if we looked into this image, you will see these brown and green contours. So these green contours are regions of enhanced moisture convergence in these layers. This layer, which works wonders, especially in the tropics and subtropics for forecasting precipitation. So we included those contours. So if you see, for example, for the Eastern Caribbean, for the Lesser Antilles, the GDI is really low. So this is suggesting that if you're gonna have convection, it's mostly gonna be shallow. You're not gonna get any significant precipitation out of this. However, if we look at, we have these green contours entering the Leeward Islands and the Central Lesser Antilles. So since we have these green contours, we can forecast trade wind showers and precipitation. That doesn't necessarily mean they're going to be heavy, but this gives us confidence that we may get some trade wind showers. Then, as you can see, we also have the flow. We have the low level flow, and the low level flow is an average of 1,000 to 850. So it will give you a general idea of how fast the trades are, where can you possibly find some troughs. So for example, we can see that there is some trough. There's a trough very close to the Cayman Islands here, and there's another trough just east of the Bahamas. Well, this looks like a front actually, but yeah. And then so the low level flow will give you the ideas of the surface features. You can see there's also another trough here, another there. And then if these features are aligned with a region of enhanced moisture convergence or GDI, then it gives you more confidence on analyzing them. So just by considering the flow and these additional quantities, we're gaining a lot of information that helps us to produce a better weather forecast. Something else that this has is upper divergence. This is the layer that works for us, 400 to 200. And whenever you see these upper divergent contours, it gives you more confidence on forecasting heavy rainfall, because some of these are related to the role of upper tropospheric features, and part of it is also related to the mono-generating strong convection. So it's always hard to define where is the boundary between those two processes. But generally, whenever you see these contours, there's a higher chance that you're going to get strong convection, and so your potential for heavy rainfall increases. And if you look at this is for 18 UTC. Right now it's only 15. But if you look at this forecast, we're showing this is showing strong convection in the northern Gulf of Mexico, just to the south of Louisiana. And you can see that the GDI is high. We're in the orange range. Then you can see that the low-level winds are converging. The black winds are converging. There's also a couple of green contours. So this is an area where there are a lot of factors producing heavy rain. And I know this is a surface front. And you also have 3 contours of the divergence, which means that there's might be very strong convection. So what I'm going to do right now, I'm going to stop really quickly and go to the satellite image and see what's going on there.
Okay, and I'll interrupt slightly.
Yes,
we have one question that came in. It's from David. It looks like he's from El Salvador. He was asking how the amount of humidity in the upper layer indicates the inversion. So
whenever you have an inversion for the, and I'm speaking mostly about subsidence inversions, you will have a sharp drying above the inversion. So you will have a very sharp relative humidity gradient across inversion, being moist underneath and being very, very dry just above the inversion. So that's what we call a proxy of an approximation to infer that you might have an elevated inversion. Just by seeing a low relative humidity in the upper troposphere, it could be a proxy for that. So then again, this is a general statement, right? You can also have other type of features, but for the most part, that's how it works. Okay, so I'll move on, and yeah, you can see the strong convection. Now we're at 15 UTC, so we're 3 hours behind the graphic that I showed. But yeah, you can see this very, very strong convection just south of Texas at the moment. So let me go back to the presentation, and yeah, this is what we're seeing on the enhanced GDI. So this is in a very, very quick manner. I'm showing you how to use this. Okay, I think I'll move on to show one more example on this, and I'll move on to the next algorithm for the sake of time. And this is another example that shows the enhanced GDI for a random case in the Caribbean basin. And we pointed out with lines, you can see these black lines are showing areas where we would expect strong convection. And if you look at the image on the left, you can see that indeed we have very strong convection along the ITCC in off the coast of Colombia and Southern Central America. This is also a northerly displaced ITCC. I think this is June, but since we have this upper trough in the Atlantic, then the ITCC has undulated towards the north, right? So just by looking at this upper trough, and then by looking at the ITCC undulated northward, we can gain confidence. Yeah, this is something that usually happens, so we can forecast heavy rainfall for Trinidad, Tobago, and the Windward Islands, and this is what we're looking at. Then this is also capturing this feature. We have a surface trough in the North Atlantic. You can see enhanced convection there, but that doesn't look that it's producing lightning. And sorry, Steve, I don't have the GLM for this, but we can look at it live in other cases once we look at the severe weather algorithms. And then you can see this area of strong convection occurring across all these Cuba and the Bahamas, and the GDI, the enhanced GDI also captured on that. So these are just examples of on how to use this. Is there any quick question on the enhanced GDI before I move into the twin?
So the enhanced GDI includes that humidity signature that you just mentioned, right? Because there was another one that came in from Sheldon, and he said, is this like the signature for the elevated mixed layer? I was thinking it might be challenging just because of if you're looking at a specific layer all the time.
Right, it's challenging. That's why the algorithms would only point you to a place you need to really make a more thorough analysis, but they won't really tell you exactly what's going on because you're fixed. Yes, you're right. So yeah, that's how this works. Yeah, they use fixed layers. Okay, I'm moving to the twin. I'm going to speak a little bit more about this one. Twin stands for Trade Wind Inversion Diagnostic Tool. Mike and I really like this one. It's been very useful for us. This has been up also for about a year. We worked on this about a year and a half ago, Mike and I. And what this does is it identifies how low the lowest temperature inversion, right, in the vertical, right? The lowest temperature inversion, and it also diagnoses the strength of that inversion. So and what you can see here in the shaded colors are the level of where the algorithm identifies inversion to be. So whenever you see these oranges and browns, it means that the inversion is really low. Is really low. And then whenever you start seeing more greens and blues, means that you might have an inversion, but it's a little bit more elevated. So in this example, we can see that we have a very shallow or low-lying inversion just to the east of the Bahamas. And then in Hispaniola, for example, the inversion is much higher. So what are the impacts of these? Whenever we see these low-lying inversions, then your moist layer is much smaller. Therefore, your potential for rain accumulation is lower. It's hard to get heavier rain if you have a low-lying inversion. Whereas whenever you have a deeper moist layer, your potential for rain accumulation increases. So this is one of the applications. And then another application that is also very important is the vertical mixing with the layer above. So whenever you have a very strong inversion, which is shown using these boxes, for example, you can see this here, and you can see these in the Windward Islands and areas to the east. So strong temperature inversions basically disconnect the overlying troposphere with the marine layer. Therefore, the vertical mixing is much lower. So whenever you have this, for example, if you have a Saharan air layer event, if your Saharan air layer has entered the marine layer and you have a strong inversion, then you need to worry about health issues because your dust is going to remain trapped. It's not going to be able to mix in with the cleaner air aloft, or vice versa, right? Sometimes the Saharan air layers are elevated. So that's one application. But it also applies for QPF forecasting. So if you have a very strong inversion, the air masses are not going to be able to mix. But if your inversion is weak, and that also happens sometimes, you have a very weak inversion, but you have a lot of dry air overlying the inversion, that's also going to limit convection because that dry air is going to mix in. Okay, so something else that we have on these charts are the mid-level flow. We have it here, right? Yeah, 700 to 400 hectopascal flow. That helps us to visualize where the mid-level ridges and the mid-level troughs are located. And these are very important for the modulation of convection, especially in the tropics. Okay, so how is inversion detected? The inversion is detected by comparing the model lapse rate, whatever the model is producing for a given point, with the moist adiabatic lapse rate. So if you see in the Caribbean basin, okay, so the moist adiabatic lapse rate represents the rate of cooling of ascending saturated parcels. So for the Caribbean basin, this is usually the range for the moist adiabatic lapse rate for the mid and lower troposphere, about approximately 2.8 to 3.5 Celsius every 50 hectopascals, right? So the inversion is detected by comparing these lapse rates, and we came out with this value, which is generally representative of the lapse rates, that whenever you see more than 2.5 degrees every 50 hectopascals, then you might have an inversion. Okay, so these are the different thresholds. So whenever, if your atmospheric or model lapse rate is more steep than 2.5 degrees, then it assumes there's no inversions present. Then if it's between these two values, between 0 and 2.5, it assumes that there's some stability. And then once the lapse rate changes sign, it means that there is an inversion. So if it's between 0 and minus 2.5, it's a weak inversion, and you start getting the small boxes. And whenever it's larger than 2.5, means there's a strong inversion present, and you start getting the big boxes. Okay, I'm just gonna move forward for the sake of time, and forward to this example. And yes, you can see that you have a mid-level ridge in this particular example, centered west of the Yucatan Peninsula, but the ridge is covering most of the Caribbean basin, especially the northern tier of the Caribbean basin. However, in this particular scenario, the lowest lying inversion is mostly in the Gulf of Mexico. You have a pocket of a low-lying trade wind inversion here in the Central Caribbean. And if you look at the satellite image, you can see that this is the NOAA cloud top height SIRA product that diagnoses the elevation of the tops of the clouds. And you can see that most of this convection is shallow, where the macro is showing this low-lying inversion. Then there's some convection in this area as well, here to the east. This convection is a little bit deeper. It's getting all the way to 750 approximately hectopascals on average. And you can see that, yeah, this corresponds, yeah, to 750 on the scale of the twin. Honduras also has some deeper convection. You can see that the inversion is also elevated, and so on. Quick examples of how to use the twin. Okay, great. I'm going to move on for the sake of time to the severe weather algorithm. And oops. Okay, this algorithm was developed. Well, initially we developed it in 2015 with Nestor Santayana, Mike Nestor, and I. We came up with GR01, as I mentioned, and then that evolved into GR02. But now this is adapted for a wider range of severe weather. Initially, it was designed mostly for detecting the potential for hail. So this is an example in the Caribbean basin, and you can see the color shades. It goes from gray to green to red. And usually whenever you start seeing these green and red color shades, it means that you have a chance for squally weather, not always hail. If mid-level temperatures are too cold, though, then your potential for hail increases. Okay, let me go forward to this. This is an example of a case in Hispaniola about actually exactly a year ago. Exactly 1 year ago, they had this hail event, mostly in the elevated terrain in Hispaniola, but some of the hail reports, which are the triangles, occurred also in low-lying areas in the foothills. And if you look at the output of the algorithm, we ran it retrospectively for that period of time, you can see that the hail occurred in this region whenever you have an overlap between the shades of colors, the little boxes, the red and fuchsia boxes inside the contours, and also you had land and orography. So orographic forcing was important. Let me move a little bit more into describing the outlook. Yeah, this is zoom, so you can see a little bit better. So yeah, whenever these factors intersect, then your potential increases. Something else that we included in the algorithm are the low-level winds, average between 925 and 850. So you can see these accelerated winds in the Caribbean. And then we also have the upper winds. This is an average between 200 and 250. So the idea of this is to give us an idea of the upper weather pattern and to detect the presence of upper jets, which have an important role on deep convection, especially when we have a severe weather risk. So in this particular case, it was very interesting because we had a shortwave trough, we have the divergent entrance of an upper jet, and then we have the environment favorable for severe convection and another shortwave trough here. Okay, so let's speak a little bit about interpretation of the macro. There are two components for this macro or algorithm or tool. And one of the components is the shades of colors. So whenever you see shades of colors, it means that a lot of different factors associated with a strong convection are present. And I'm going to show them in a little bit. So whenever you see grays, it usually means that you have a potential for strong convection, not necessarily severe, but you need to watch out. Then whenever we start getting into greens, we're still calibrating the algorithm, and again, these algorithms are perform a little bit different depending on the latitude and geographic location. But for the most part, whenever you start seeing greens, then you start seeing a marginal to slight risk of severe convection. Then once you start seeing reds and fuchsias, you need to worry. Or worry to look into other model data, right? And you cannot just go blind with the algorithm output, but that will point you that something bad could happen. So this is one aspect, and then the other aspect of the algorithm are the boxes. Whenever you see color boxes, this came from the initial hail algorithm. So these boxes represent that you have an environment where your lapse rates are very, very sharp in the mid-troposphere, and you have a lifted index that is quite negative, and then that you have omegas, ascending omegas in the mid-troposphere. So this is usually favorable for hail. So what I'm showing here on the left is the forecast for the severe weather event that happened yesterday in the Southern Plains in Oklahoma, Texas, Arkansas, and Missouri. And this is the output of the algorithm. And yeah, look at it. It's showing the shaded area that is fuchsia, so elevated risk. It is showing also boxes inside the color contours, which is showing that a potential for hail is present as well and is consistent in location. And if we look at these two different this progression, we have 18 UTC first, and then we have 00 UTC in the second graphic. We can see that the potential initially develops in southeast Kansas, and then it goes all the way into northern Texas and Arkansas later in the day. So something that is also important to consider is the time of initiation of convection. You might have a favorable environment. The macro might be showing something massive, but if you're in the wrong period of the diurnal cycle, or if there's nothing triggering convection at the time, that environment is going to be inutilized, right? Sometimes we see these large values very early in the morning, like 12Z, 15Z, but it's too early for convection to develop, so nothing happens. So that's also important to have in mind. When do you think that convection is going to develop? Something else to keep in mind is the use of these yellow contours. As you saw in the enhanced GDI, these are also the upper divergence, enhanced upper divergence. So whenever you see these contours appearing suddenly, it's suggesting that the model is resolving very strong convection forming. So this could be a way to have an idea of initiation. And of course, you have to compare it to other tools. So if I were to put together a semi-blind forecast, just looking at this, because you need to look at other things, right? If I'm just looking at this and want to put up a quick forecast, so my area of severe convection will be this, right? Will be Eastern Oklahoma, southern Kansas, all the way into Arkansas, because if you see the next time frame when you get the initiation, it's extending all the way there, just by looking at this. And if we look at the reports from yesterday, yeah, indeed, this is the area where most of the severe weather reports were present. And if you take a look at the hail reports, the hail reports occurred mostly to the west. There were some reports in Arkansas, but most of them were in Oklahoma, and this is consistent with where you see the boxes in the algorithm. Okay, so how are the shaded areas constructed for these algorithms? Again, you'll have this presentation, so I'm just going to try to go a little bit faster with that. First, what we do is we define something that we call a strong, deep, moist convection mask. So what we do, we would look at 5 parameters that that will tell us that if there's a potential for deep moist convection to develop. The 5 parameters that we've been playing around and ended up deciding that were useful are these 5. We have precipitable water. Whenever we're assuming that whenever you have more than 20 millimeters, there's sufficient moisture to allow for deep convection. That's been working for us. Then lifted index below 0. We're just looking for deep convection. We're not looking for severe yet. So we're using this threshold. Then this temperature works for us, 600 temperature plus 2. So this speaks about the presence of strong up, the potential for strong updrafts, right? Mid-levels, instability if you have cold air in the mid-levels. And also the cold air will favor the hailstone being closer to the ground. So it will be easier for it to reach the ground as ice. Then we're looking at relative humidity higher than 80, which is suggesting that you have saturation, which is favorable for cloud associated with the storms, also for the growth of hail. And then omegas, right, in this layer. This layer works well for us, 600 to 300. Well, yeah, I'll have to check on the 6 versus 7. But we look at these 5 variables, and whenever we are exceeding the thresholds, we place a 1 in the mask, and whenever these don't reach the thresholds, it's just 0. So whenever we see 1s in this mask we just built, means that these 5 parameters and thresholds are present. So once we have these masks for severe convection, what we do is we populate them with what we're calling enhancers of severity. So only inside these masks where we have the 1s, we grab all the lifted index areas that are below 0 Celsius, meaning instability, and then we populate that with values. And these are weighted functions that we still need to tune up, but they're working for us. So we look at the lifted index. We look at the lapse rate. This is very important, and this is very important for hail, particularly the 700, 500 lapse rates. We look at 500 temperatures. We use -8 for the algorithm to populate the mask as a threshold. So the temperatures are warmer than that, it doesn't do anything. Then we're looking at omegas in the mid-troposphere as well. Then in this case, we're also looking at shear. And for those into severe weather forecasting, this is a very, very general approach. So what we're doing is we are averaging the 1 to 3 kilometer we're averaging the 0 to 3 kilometer shear with a 0 to 6 kilometer shear. So this is a very simple approximation. And also there's a threshold whenever for high shear. Whenever you have too much shear, you tend to destroy the storm. So we haven't implemented that. So far we're working with this, and it's working for us. Then we also have the low-level moisture convergence and the upper divergence. So this is very general, given that our forecast domain region is very large, but it's working for us. Okay, going back to the example that I was showing for yesterday's event, if you see, this is Monday's initialization of our algorithm during the convective initiation period, and SPC's official forecast was this. Of course, initially you need to be cautious when you're forecasting something severe, because you don't want to overwarn, right? Make people too scared, generate panic. You need to gain confidence as well. So their forecast was this, and it was nice that it kind of matched our algorithm output, meaning that the algorithm seems to be working. So the official forecast is consistent with it. And once we moved to the day of the event and SPC was able to refine their forecast, yeah, that was very fulfilling for the science of the algorithm, because as you can see, it matches the algorithm fairly well. And once again, the reports are consistent also with what the algorithm was showing. Let me show a couple of quick examples for South America. We have a ton, but these are recent ones. This is for an event that happened actually yesterday as well, as Oklahoma and Texas were getting severe weather. Argentina was also getting severe weather. And this is the hail that they got. They got a lot of hail, and as you can see, pretty big. And this hail occurred in this region, where you can see the red boxes and red contours located over a shaded area. So there's a potential for severe weather, but it's also specific potential for hail, since you have the boxes and contours. And if you can see, you also have these enhanced upper divergence, which are the yellow contours in the region. So yeah, the macro has been very successful in South America. This is just one event, but Nestor and Manuela Sanchez can attest to that. I mean, we have very good feedback from South America. This is another quick example of the macro for another severe weather event that happened a couple of days ago in the southern U.S. This was the official forecast moderate risk for all the Gulf Coast, basically. These are the reports. You can see there's mostly wind. The hail is mostly favored west, which is part of the climatology of the region. But there's a lot of severe weather reports and even tornadoes. The macro is not specifically designed for tornadoes. It will just speak about the chance for squally and severe weather in general. But in this case, there were tornadoes. And you can see that the macro generally showed the potential pretty decently. And you can see that at the beginning, the potential for hail is much larger to the west in Texas, where it occurred. Whereas further east, there was a little bit of potential for hail, but it was mostly shaded areas, which are general severe weather threats. Okay, so this is the fourth algorithm. This is also being used quite a bit in the Americas, and people have mentioned they're happy with it. I know TAFB is using it as well in the National Hurricane Center. And this is an algorithm to help us identify surface fronts. Sometimes they're challenging. So we started working for the Caribbean basin. Most of our efforts are for them. But then we expanded to the rest of the continent. And fronts, once they get to the tropics, they are different than mid-latitude fronts. They're sometimes are harder to find. Sometimes they're easier, but for the most part, they have lower baroconicity, so weaker thermal gradients. They're also shallower, so sometimes they're invisible and 850 hectopascals. So you need to look even further down. Moisture fields matter a lot. Sometimes the thermal change is going to be really, really weak, but you're going to get a sharp drying, so that's the way to find them. And then also there are some geostrophic peculiarities, but that depends on the geography of the region. Since I have little time, I'm going to show you what the algorithm has. So we've been playing around with different variables, and for subtropical and tropical locations, these are the ones that we realized that work, at least so far, working better for us. We're looking at 1,000 to 850 thickness and not 1,000 to 925 thickness. So this speaks about thermal aspects of the front. And then we're also looking at the moisture aspect just by looking at dew points. I notice that we're looking really low in the troposphere because once the front gets to the tropics, are really shallow. Then the quantities are multiplied just to enhance the visualization of the front. Again, I mean, we're not doing rocket science, but we want is to help the forecaster to see things, right? So yeah, we decided to play with different mathematical operations, and just by multiplying these quantities, we get a very decent visualization of the front. Might be. Once we have these quantities multiplied, we call this alpha, or a field called alpha, and then we will calculate the magnitude of that field. And also we calculate the magnitude of precipitable water and theta E. So this is the quick look of what we do. But basically that helps us to highlight the frontal gradients. Let me go to an example of a front in South America. So if you see on the right, whenever we see these black areas, and when you start getting these light blue contours, yellow, and then fuchsia means that you have a very sharp gradient in this field that we call alpha, right? So if I were to analyze the front, I will analyze the front along this gradient and maybe a little bit to the north. And then we have the southerly flow. So whenever we have southerly flow, the front can be slightly further north than what the algorithm shows it. So we also need to keep an eye on that. The flow is 1,000 to 925 flow. So it's showing the low level flow. Okay. So this is where we will place the front. And if you look at the satellite image on the left, there's a lot of clear skies in Central South America. However, in Western South America, you can see all this stratiform cloudiness, which is typical of a postfrontal air mass. So the front actually went pretty far north. Went all the way. This is 5 degrees south. So it's almost in the equator. Fronts do that in South America. Something else that we notice is that actually the algorithm, this is one time after, like 6 hours after the previous graphic. If you look at the algorithm, this is showing the front and the Peru-Brazil border, which is here. But looking at the observations, the station showed that the front was even further north. So I've noticed that personally lately when doing the forecasting in the tropics. If you have strong surface flow, the front may be a little bit further closer to the equator than what the macro is showing. So that's something we need to consider among other feedback to improve the algorithm. So don't just go blind by placing the front where you see these black magnitude of the gradient, but you need to sometimes think a little bit further. And in this case, the front was a little bit further north from this enhanced southerly flow. And the one variable that captured it was the thickness. So sometimes the thickness is better, sometimes the moisture is better. All right. And a last example with this, that I'm going to show with the front. This is also sent by Nestor today. This is what happened in South America. This is yesterday on the left, and this is today. And you can see the very book-like looking extratropical cyclone with the triple point, the occlusion, and then you have the cold front that is reaching northern Argentina. And in the satellite image, you can see this, right? You can see the same thing. The projection is a little bit different, but yeah, you can see the structure. Of course, this is an easy one, right? Then you can also see the one in Chile. You can see this, and you can see actually the frontal waves. Sometimes the gradient will not be plotted because maybe it's weak, but that's why we have other fields overlaid. We have surface winds, we have the alpha field, which is the color field, and then we have 1,000 to 800 thickness. So all these different things will help us to find where the features are. I think I can speak about CAPI in a different time. I only have very few slides on this. But given that we're running out of time and actually the rainy season is ending in South America, I'll probably put more emphasis on this in another time. So I want to open up the session for questions.
Okay, thank you, Jose. We do have one that came in earlier from, let me scroll up here. It's from Carlos Colombana, and I believe he's in Uruguay. And he said, could the algorithms be adapted to work with WRF instead of the GFS?
The answer is yes. Yeah, definitely. You can adapt the algorithm to work with anything really. We did that with the GDI. Thanks to Mark Klein. Mark Klein coded the GDI for the European model, so the same can be done with these ones. However, some of the algorithms might produce a different output because I don't know if you understand the term, but each model has a climatology, given that the model has a particular bias. So you will need some adjustments to be able to produce a similar result, but it should be able to be coded anywhere.
Okay, and another one, would it be possible to have the GROW2 based on the K index or the GDI in order that they can compare which one suits them better? So like, yeah, and Kathy Ann had a similar question. You know, there are other indexes that are being used, and I know that I've heard you and Mike talk about this in the past. So perhaps it's another aspect for the future. How do these indexes compare with some of the existing ones, such as the K index or the lifted index?
Great. Yeah, you can look at them together, but I don't fully understand the question. If you can combine, could it be possible to have a GR02 based on the K index or GDI? Well, the physics are very different. Is Kathy there? Hi, Kathy. I'm reading your question about the GDI and K index and GR02.
Yeah, because when we looked at the LI in the Caribbean, it wasn't as good as the K index in determining severe weather activity. So I was wondering, you already have in your algorithm the relative humidity at each 50 millibars, which actually kind of mimics what is done in the K index. But if it's possible, can you replace the LI with the K index and for the tropics itself? Would that be
I mean, we
viable?
I got it. Yeah, we could play with something like that. But the emphasis of the hail algorithm is mostly for gusty weather and severity and hail. So yeah, in the Caribbean, I guess it's much more common to have a threat for heavy rain, and that's where the K and index and the GDI jump in. So the hail, the severe weather algorithm doesn't necessarily speak about heavy rain. It could tell you about It could tell you about large rainfall rates, but it's more targeted for saying, oh, we're going to have gusty, squally weather than rainfall amounts. I mean, we could play with it, but yeah, the idea is something different that we're looking at. Yeah. Did I answer your question?
No, that's perfect. That's perfect, and really compliments on these indices because the results look incredible. So we'll look forward to actually kind of, we have a forecast class starting in a couple of weeks. So we'll be definitely looking at them. Thank you.
Okay, great. Thank you, Kathy.
So we have one from Rosario.
Yeah. Rosario.
Products run in different domains. She says, thanks. It will be beneficial for many countries. What's the finest resolution available?
Okay, great. Yeah. Given the computer resources that we have at the current time, because we have 2 PCs allocated for running these, we're using 1 degree resolution. So we could also do that for finer resolution. The only domain we're using finer resolution for is the Puerto Rico domain, since we have an important role on forecasting QPF for them. But other than that, we're running everything with 1 degree GFS. So these can definitely be made available at higher resolutions. It will just require some extra work, and it will take more time for the algorithm, for the graphics to be produced. But also something that you need to keep in mind, especially for algorithms that consider quantities that are constructed with differentials like convergence and vorticity and so on. The output will change a little bit if you go to higher resolution, because those fields can be noisy. So we need to play a little bit with filtering the data and smoothing the data. But yes, it could be done in the future, definitely. If someone has a particular interest, yeah, it could be done higher resolution.
And this perhaps leads a little bit into the next question by Juan Jose in El Salvador as well. First, he asks also, do you have the algorithms document? And that might mean not only what it is, also, I think you have wind grids on how to program it up. So that could be two things.
Yeah, the answer to that is quick. I do not yet. Wherever we coded the algorithms in wind grids, I try to be, again, I want to acknowledge Mark Klein, because I've been reading Mark's scripts, and Mark is really, really detailed and organized. So I've been trying to be as organized as Mark and document everything when I code for wind grids. So there is kind of documented, but I haven't had the time to put that into a nice PDF that looks more like a journal article. So not yet. We're still developing that. Yeah.
A second comment is, with you suggest, or would they need to adapt it? The algorithms for like specific regions, just as you've been doing?
No, that's why we have some of the products implemented for certain domains and not for others. This is one thing. So for example, the severe weather algorithms don't work in the deep tropics. That's then the trade wind inversion, it's irrelevant in southern Chile or Argentina. And then within specific areas, for example, El Salvador is at the same latitude maybe as let's see, could be Hispaniola, for example, Dominican Republic, but the geography is a little bit different. So that's why we need the user feedback to help us validate, verify these algorithms so we can improve them and make adjustments that can be a little bit more general. And this is one of the challenges that we have because, as you know, our forecast domain is very diverse. So if you're trying to fix an algorithm for a region, but then you're messing it up for another region, so it's always challenging to try to find a balance for that. Yeah.
Although I'll add from the education and training perspective that encouraging people to think about how the algorithm fits and what to adapt is really good and helps you plan ahead.
Yeah, that's why this should be a group effort because people in the regions they know better the climatology, they can have ideas to improve the algorithms locally, and this has actually been done before. I don't know if everyone is aware that the group in Cuba took the GDI and makes a couple of minor changes to improve them. They change the threshold because sometimes they get these very cold upper troughs and they can get a lot of severe convection, but the threshold of the GDI was too low. So they changed that and they got better results. So definitely, yeah, I encourage people that are working on science and looking at data every day that, yeah, come with ideas and propose it to us, and maybe you can even take it and do it yourself. Yeah.
I don't see any more questions at the moment, so I'd like to just say thanks, Jose. That was a great presentation.
Great. Thank you, Bertie. Thank you, everyone, for taking the time to attend the presentation. And yeah, if you have any questions, just send me an email and we'll be happy to address the questions the next coming days. Thank you very much.